Hello everyone. In today's video we are going to be looking at Newton's laws, all the Newton's laws. We're going to discuss all the Newton's laws, the non-contact forces, contact forces as well, because these are the forces that we are going to be actually applying on our Newton's law, mostly on Newton's second law. So we're going to stick a lot more on Newton's second law calculations, these are the mechanics. Look, grade 12s, just before we start, I wish you a very good luck to your academic year. I know metric was never easy, because metric is challenging. So I wish you a great resilience, etc. Also to grade 11s, because the Newton's laws, we introduce them in grade 11, so some of them might be here. So I also welcome you guys, just like matriculants. Lastly, what do I forget? Please don't forget to subscribe. Please don't forget to subscribe. Please don't forget to share. And thank you so much to those who have already subscribed. And again, this is our very first video this year for all subjects, by the way. Yes, but fundamental for physical science, because we're going to be dealing with today physics. Thank you so much. Let's get into the topic. Okay, so guys, I'm just going to try to be slow as possible, okay? Yes, no need to rush for me. Okay, so as I said, we're going to first discuss forces, okay? Yes, because we have a lot of forces, but we're going to make it sure that we only discuss the forces that are being used mostly on Newton's laws, okay? Yes, so as I already told you that we have contact forces as well as non-contact forces, okay? Yes, so we have contact forces and non-contact forces, okay? So a contact force must touch, meaning that there must be a physical touch between the applier and the object that the force is being applied on, okay? Yes, so there must be a touch or be in contact with an object to cause a change, okay? Yes, for example, okay, of contact forces. So contact forces can be the force that is being used to push or pull things, okay? Yes, that's a contact force, because in order for the movement or for the change of a certain object, there was a contact, okay? A touch, which can be a pull or a push, to emphasize. Okay, moving. The force that a sculptor uses to turn clay off a pot, for instance, okay? Yes, because there's a touch when you're making something using your hands. There's a force, there are forces that you apply to make the object. And lastly, for instance, the windmill to turn, okay? Yes, so the wind forces the wheel to move, okay? There's a touch there, so it doesn't just move, okay? Yes, there must be a wind somewhere touching the wheel so that the wheel can move, okay? So these are types of contact forces, okay? So but mostly put this in mind when you're speaking about contact forces. If you want to be aligned mostly to Newton's laws, you must know this is a pull or a push, okay? Yes, there must be a contact. Okay, moving. So we also have non-contact forces. So non-contact forces does not have to touch, okay? There's no need for the applier to touch, okay, the object. So for instance, the non-contact forces are the forces that like due to gravity, like the earth pulling moon towards itself, you being pulled by earth to the ground. Electricity, magnetism, etc. Okay, yes. So in terms of electricity, this is like a proton, I can say, and an electron attracting each other to cause a charge. In magnetism, this is like a magnet, okay? If you put a magnet when they are pulling each other, okay? Yes, towards, maybe we can say, yes, south pole, north pole, they pull each other, okay? Yes, so that they can be in contact. So if they pull each other, there was no one, I didn't push this magnet on the right hand side and push this one so they can touch each other. I just put them here, they just do by themselves. So these are types of non-contact forces. Okay, I think now you understand. Okay, so let's have these type of forces here. Okay, yes, let me write forces here because we are discussing forces. Okay, yes. Okay, so let's draw. Okay, let me not draw here, let me draw here, let me draw here. Okay, this is an object. Okay, this is an object, and let's say this object, it's on the surface or on the land. Okay, yes, it's on the surface. Okay, so there are forces that are acting on this object. Okay, so to first discuss and name these forces that we are going to be dealing with mostly on Newton's laws. Okay, so we have an applied force. So this can be pull or push, meaning that's a contact force. Okay, yes, if I'm pushing this force this way to the right side, okay, if I'm on this side, I'm standing this side, I'm pushing it this way, so this is gonna be applied force. Okay, this is the applied force. This is the applied force. Okay, this is the applied force. Okay, so in this object is not flying. Why it's on the surface and why it's stable? Okay, just forget that I applied a force in this object, but I'm asking yourself if why this object is it's on its rest, meaning that it's not flying, meaning that vertically. Okay, yes, it's because there's a force that is acting on this object downwards. Okay, yes, pushing it downwards, and it's called gravitational force. Okay, yes, the gravitational force is it's a non-contact force. Okay, yes, so this is gravitational force. Okay, yes, so this is gravitational force. Okay, not to confuse you again, we also have another force. Okay, so if gravitational force is acting downwards, why then this object doesn't sink underground, or it doesn't change the shape, meaning that it doesn't get squashed? Okay, it's because there's also a force that causes balance here, which is called the normal force, which is acting perpendicular from the ground or from the surface. Okay, yes, and this is the normal force. Okay, this is the normal force. Okay, mind you, normal force is acting perpendicular from the ground, 90 degrees. Okay, yes, opposing what? Opposing the gravitational force. Okay, so also I have a force that is called a frictional force. Okay, mind you, a frictional force, it can be a static frictional force, or it can be can be a kinetic frictional force. Okay? Yes. So I'm going to explain what happens when it's static and what happens when it's kinetic. Okay. So this is frictional force. Okay? Yes. With a small f there. Okay, this is frictional force. Okay? This is frictional force. Okay, yes, so this is frictional force. Okay, so okay, we also have things like tension force and so on. Okay, yes. Okay, so a tension force, this is whereby if ever I'm pushing this object this way, okay, I'm pushing it this way, this is the applied force. Okay, applied force, I'm on this side pushing this object to move this way. If this object, let's say maybe this object, or there's another object that is connected from this object, okay, like this, let me draw it, yeah, okay, let me draw it here, let's say this object is this one, okay, yes, this object is object X, okay, is pulling object Y. So there is a force acting between this object and this object. There is a force acting between object X and between object X and object Y, and between object Y and object X. This basically means that there's a force here and there's a force here, okay, because this is a string, okay, yes, and we call them inextensible string, okay, yes, so this string is inextensible, meaning that it doesn't extend, okay, yes, it's just strong as it is, okay, yes. So as I said, there's a force acting on X and Y, meaning that X is pulling Y, okay, yes. And if X is applying this force, simultaneously Y is also applying that force, but we're going to discuss that mostly on our Newton's third law. Okay, so meaning that this is I just wanted to show you the tension force, okay, yes, so the tension force, okay, we have tension force, and this is how we write it, okay, this is tension force, okay, yes, okay, so I said to you, so that I don't forget, I said to you, in frictional force we have a kinetic frictional force and a static frictional force. So this is going to be your this is how we write your frictional force, static frictional force. This is a static frictional force, okay, yes, static frictional force, this is how we write it, okay, and this is your kinetic frictional force. Okay, let me explain what's the difference in between these frictional forces. Okay, and so by defining frictional force, this is the force that opposes the motion of an object in contact with the surface, and it acts parallel to the surface the object is in contact with, meaning that if this object, I push this object and this surface is frictionless, okay, yes, so this basically means that there is other force that is opposing this object from moving, okay, yes, moving. If I'm pushing this object this way, there's other force which is called frictional force that pushes it or slowing it down, okay, yes, to the left, the left hand side. Okay, so in terms of the static frictional force, this one, okay, yes, so this is the force, this is the frictional force that stops an object from moving, okay? Or this is the force that stops the tendency of an object from moving, okay? Yes. So static frictional force is only acting on an object that is at rest, I can say, okay? Yes, on a non-moving object. So a kinetic frictional force, it's a vice versa, okay? Yes, this is a frictional force that acts on a moving object, okay? Yes, parallel from the ground, okay? Yes, opposing the motion to stop the object, okay? Yes. So going back to static frictional force, as I said, this is the frictional force that stops the object, the tendency of an object from moving. Okay, this basically means that an object will always at rest, okay? Yes, it will always at rest unless if I touch it, okay? Yes, like this. So if the static frictional force is being overcome by the applied force, meaning that the object will suddenly move, and when it carries to move, the kinetic frictional force gets in. I think now you understand. So they have the same formula, okay? Yes, but different conditions. Okay, so okay, so we also have, okay, so this is mu, static frictional force, okay, to the normal force, okay? Yes, so this is mu, okay, normal force, okay? Yes, so these are the formulas looking the same like that, okay? Yes, for the static frictional force and the kinetic frictional force. I think I've nailed it, okay? Yes. So this, the mu k or the mu s, okay, this is mu. This is mu, okay? Yes. And this is a Latin word, okay? Yes. This is a Greek word, I mean, it's a Latin or Greek. So yes, so this is a Greek word. This is a Greek word, by the way, yes. So mu, this is the coefficient, okay? Mu is the coefficient of frictional force, okay? Yes. So you'll see how we use mu, okay, or how we apply mu in our calculations. So again, mu, okay, so again, mu stands for the roughness, I can say, for the roughness of the surface, okay? Yes, of the surface. Okay, so mu stands for the roughness of the surface, and again mu is the coefficient of the frictional force. Okay, moving. Okay, so we said we also have a normal force which is acting perpendicular from the ground or from the surface. Okay, so yeah, that's how it goes. So let me now introduce you to Newton's laws, okay? Starting from the very first Newton's law, okay? Yes. Okay, again, before I introduce you to the very first Newton's law, mind you, as I said, mu stands for the roughness, or it stands for the roughness of the surface, okay? Yes. So meaning that the higher the roughness of the surface, meaning that there's a lot of friction right now, okay, against the object, okay, yes. So meaning that there must be also a higher applied force to move the object. So the lower or the smoother the surface, the lower the amount of the applied force to be applied on an object to move the object. Okay, yes, I think you get me. Okay, so let's get into the very first Newton's law. Okay, yes, so this is Newton's first law. Okay, so let's get to Newton's first law. So this is Newton's first law. Okay, so Newton's first law states that an object, okay, so an object continues in a state of rest or in its uniform motion with a constant velocity, okay, yes, so the uniform motion is a constant velocity, okay, yes, so unless it is acted upon, okay, or unless it is acted on by unbalanced net force, okay, yes, so an object will remain at rest, okay, yes, or an object will continue on its uniform motion unless there is a resultant force acted upon an object. Okay, so that's Newton's second law. So meaning that in Newton's first law, okay, think about this, okay, under Newton's first law, okay, this is an object, okay, let's say this is an object that is at rest. This object will always be on rest unless there is a net force applied on it, okay, yes, so this object will only move if the net force is applied on it, okay, yes. So again, let's make an example of a car. If we say an object will be in its constant motion unless a net force is applied on it. Okay, let's say this is the car. This is your car. And here you have the passenger, okay? Yes. You have the passenger here. This is your chair. Okay, this is your passenger, okay? Yes, this is your seat. So, moving this way, okay? So, a passenger in the car will also move the same speed as the car. Let's say the speed of this car is it's 120 kilometers per hour, okay? Let's say this is 120 kilometers per hour. You as the passenger inside, you are also moving 120 kilometers per hour, okay? Yes, you're moving at this velocity, okay? Yes, and this car, let's assume it's moving on its constant velocity, which is 120 kilometers per hour. So immediately the time the driver applies the brakes of the car. So you as the passenger, the brakes are only applied from the car, not from you. You don't have the brakes. So this basically means that you will tend to continue with the motion to move with the 120 kilometers per hour. That's why we have safety belts. I think you do understand. So again, if you have, let's say, a car, let's say this is a car, okay? I'm just going to draw the top view of the car. Okay, so it's turning here. Okay, yes. It's the road, it's the car. You're here as a passenger. Okay, yes. You're here as a passenger. So, if this car So when it turns here, okay, yes, so when the car turns, again, the car turns, you run 10, and you're on the same speed as car. So if this car turns, when this car eventually turns in this 10, so you as a passenger, you are going to turn to move in a straight constant velocity. So meaning that if this car was moving or was turning this 10 by 60 kilometers per hour, meaning that you're going to accelerate, okay, you're going to tend to move, your body will tend to move by 60 kilometers per hour straight. So in the car it will seem like you want to go this way, okay, yes, it's like you want to swerve like this way, okay, yes. So this basically means that that's the reason why the passengers are being thrown away when the car is turning, okay, yes. So I think you do understand Newton's first law. So let's get to Newton's second law. So Newton's second law. Okay, so Newton's second law states that if a net force acts on an object, okay, so the object will accelerate, okay, or it will cause the body to accelerate in the direction of the net force, okay, yes, and therefore the acceleration of the body or the acceleration of the object will be directly proportional to the net force and inversely proportional to the mass of an object. Okay, again, okay, sorry, okay, so Newton's second law states that when a net force is an applied force, okay, yes, a net force, okay, all the forces that are applied on an object to move. So a net force, when a net force is applied, on an object, the object will accelerate in the direction of the net force. So for instance here, okay, so when a net force is applied on an object, the object will accelerate in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the mass of an object. This basically means that when this net force, okay, let's say this is net force, okay, so this is our net force. This is our net force, okay, this way, and our net force is pointing us this way, meaning that this object is being pushed or pulled or whatever the case may be to this way, to the right hand side, as you can see the arrow. So this basically means that the object will accelerate in the direction of this net force, yes. So yes, in the direction of this net force, okay, yes, and the acceleration is directly proportional to the net force and inversely proportional to the mass of this object, okay, yes. An object have a mass, okay, you should know that, okay, but all forces, okay, or I can say forces, we represent forces by Newton, okay, yes. So you should know that these are the units for the forces, okay, yes. And for the mass of this object or each and every object that you are going to see on your scenarios, it's kg, okay, yes. If it's grams, okay, you should know that if it's grams, you should take it to kilograms, okay, yes, by dividing it by 100, okay, by 1000, I mean, yes, I think 1000, yes, 1000. Okay, so this is a mass, this is, oh, it's acceleration right now. Okay, yes, it's acceleration. This is how we write it. Okay, yes. Okay, let me just say acceleration. This is acceleration. This is how meters per second squared. Okay, yes. So that's how it goes. Okay, so going back to this object, so this basically means that, okay, again, when a net force is applied on an object, the object will accelerate in the direction of the net force. Okay, yes, the acceleration is directly proportional to the net force and inversely proportional to the mass of an object. Okay, so if the acceleration is directly proportional to the net force, okay, to the net force, and as well as the acceleration is inversely proportional to the mass of an object. Okay, this basically means that if we increase what? The net force, the applied force, okay, the force that caused this object to move. This basically means that the acceleration will also increase. Okay, yes. If I increase the net force, the acceleration will increase. So if I'm pushing a bus alone, okay, and it moves, and some 4 guys come and help me to push this bus, meaning that there is an increase in the net force, meaning that the acceleration will increase. The acceleration of the bus will increase, the bus will move faster now. I think you get me. Okay, so in terms of the acceleration being inversely proportional to the mass of an object, this basically means that the higher the object, okay, the higher the object, the higher the mass of an object, the lower the acceleration. Okay, this is the lower the acceleration. The higher the mass of an object, the lower the acceleration. Okay, yes. If the object is the mass of an object is high, this basically means that the object is heavy. Okay, yes. And if I'm 1 in this object, it will move slower. That's why the acceleration is downwards. But if the mass of an object is weaker, I decrease the mass of an object, the acceleration will increase. I think you get me. Okay, that's how it goes in terms of the net force. So let's derive the formula. Okay, yes, the formula. Okay, so this is the formula, and where it comes from, comes from this. Okay, yes, it comes from this. Okay, so therefore, if the acceleration, okay, just so the formula comes from here. Let's derive the formula. Okay, if this is inversely proportional to the net force, this basically means that and also if acceleration is inversely proportional to the mass of an object, this means that the acceleration is equal to the net force. The net force, yes, acceleration is equal to the net force over m, over the mass. Okay, yes, so the acceleration is equal to the net force over mass. So let's cross multiply. Okay, this is over 1 this side. Okay, yes, let's cross multiply. We have F net this side. The net force is equals to A multiplied by M. This is our MA. This is our formula for Newton's second law. Okay, yes, in our calculation we are going to be using this formula. Okay, so this is the net force, all the forces acting on an object, and this is the mass of an object. This is the acceleration. Okay, moving guys to the Newton's third law. Okay, so sorry. Okay, so we have our Newton. Let me not write faster because my writing is so bad. Please forgive me guys. Newton's third law. Okay, yes, this is Newton's third law. Okay, this is Newton's third law. Okay, this is our Newton's third law right now. Okay, so Newton's third law states that if body A exerts a force on body B, okay, if body A exerts a force on body B, then body B will exert a force of equal magnitude on body A, but in the opposite direction. So this basically means that the Newton's third law states that if body A exerts a certain amount of force on body B, then body B will exert a same equal amount of force to body A, but in the opposite direction. Okay, for instance, for example, this basically means that when it's you, okay, this is the wall. Let me just draw the wall on the table. Okay, let me just draw the wall. Okay, this is the wall. Okay, yes, it's the wall, and this is you. This is your hand to the wall. You are pushing the wall. Okay, yes, so you are pushing the wall. The other hand is here. So you are pushing the wall. Looking this side, you are pushing the wall. So if you're pushing this wall, you're exerting a force here. Okay, let's say this force is the applied force is equal to let's say 80 newtons. Okay, yes. So if you're exerting 80 newtons on the wall, also the wall is exerting 80 newtons back to you. Also the wall is exerting 80 newtons back to your hand. Okay, back to your hand, I mean, yes. So this basically means that if your hand pushes the wall also pushes you with the same magnitude. Okay, yes, but in the opposite direction, as you can see, opposite direction. Okay, yes. So this is Newton's third law. And if I put this on top of the table, why it doesn't fall? It's because the table is avoiding it from falling by pushing it upwards. Because if I put this my pen on top of this table, or let's say it's a book or the pen, as you can see, so that if the pen is pushing the table downwards with a certain force, okay, but also the table is pushing it upwards. Okay, yes, so there is a force of gravity acting on this pen, pushing it downwards. Then there is a force, a normal force, pushing it upwards. So that's why it's stable, that's why it's not falling, it's not flying. Okay, yes. So let's say like this, that was the gravitational force pushing it downwards, and the normal force pushing it upwards. So it stops now. So again, so sorry guys, I should have told you this in the very first stages. Okay, again, so what I want to say to you is that sorry, let's fix something here. Okay, so when, okay, let me write it here. It's just a note, guys. Okay, yes, it's just a note. Very, very important. Okay, when an object is at rest, when an object is at rest, this basically means that the object is experiencing no force, meaning that the net force is equal to 0 newtons. This is very important, guys. So for example, let's say this is let me start with an object that is at a horizontal surface. So this basically means that the net force is equal to 0, meaning that the forces, either forces acting on this side or forces acting on this side, okay, to this side or to this side, let's say they come up to 0, meaning that the net force is equal to 0 newtons. This object is stable. Again, if let's draw a table. Let's draw a table. And now, guys, I'm just introducing you back to the calculations regarding Newton's second law. Okay, yes. So this is the table, and this is my book. This is my book. This is my book. So this book is stable. You can see it's not sliding, it's not falling, and so on. But I'm just regarding the forces that are acting vertical. So I said to you, there is a force of gravity acting on this book, pushing it downwards. Okay, pushing it downwards, and also the normal force. The normal force, which is the force that is being applied by the table to the book. Okay, yes, this is the normal force. This is the gravitational force. Okay, yes. So meaning that the normal force and the gravitational force, the reason why this book is not falling downwards, okay, or this book is not flying, it's because the net force and the normal force and the gravitational force are at equilibrium, meaning that they are equal to 0 Newton. Okay, yes. That's how it goes. So you should know that the gravitational force or the normal force is always opposing the gravity. Okay, yes, the gravitational force. So that's why it's stable. Our book is stable. I think you do understand, guys. Let's move to the calculations right now. And also now your calculators must be ready. Okay, yes. So let me just do like this. Okay, let's do like this. Okay, so okay, this is the net force. Okay, equals to 0 n here. But I'm just going to show you how the using these two forces, the normal force, the gravitational force in particular, to show you how they gone to 0 n. Okay, yes, I'll just show you guys. Okay, so okay, let me show you now. Okay, let me show you now. Okay, so I said to you the reason why this this object, this book, is stable here. Okay, yes, because the net force acting on this book is equal to 0 newtons. Okay, mind you, the net force, this incorporates the normal force and gravitational force under the net force. Okay, so this basically means that the net force is equals to 0n in that situation. So the net force incorporates your normal force, okay, your normal force. Okay, let me just write F. This is Fn, guys. Plus, okay, the net force. These are all the forces. These are sum of all forces acting on an object. That's why I put the addition sign, which is plus gravitational force. Gravitational force is minus. Wait there. Why gravitational force is minus? It's because you should know that each and every force that is acting downwards to the object is negative, and each and every force that is acting upwards to the object is positive, and each and every force that is acting to the right side or to the east side to the object is positive, and the one that is opposing the motion to the left hand side, such as friction, it's a negative sign. Okay, yes, we're going to minus them. Okay, yes, they carry a negative sign. So that's how it goes. So again, let me emphasize this so that you cannot get confused, because in some situations you would find out that the force being applied on this object, okay, let me write, this object is pushing this object this way. So the applied force now it's on this way. Let's say this is a friction, okay, friction is there, okay, yes, is present. So meaning that the frictional force is going to oppose the motion, is going to oppose the applied force, meaning that this is going to be minus, because it's opposing the motion. Okay, yes, that's why I had to emphasize and re-explain regarding this scenario when it's acting horizontal. But in vertical situations, it's always like this. The gravitational force is always minus, and the normal force is always plus, meaning that is positive. Okay, so going back to the findings here. So the net forces acting on this object is the normal force, the gravitational force. They are equal to, I said equals to 0, right? Yes, equals to 0. Okay, so this basically means that the normal force is now equals to gravitational force, because I took the gravitational force to be on that side. Okay, yes, so that's how it goes. Okay, yes, so that's how it goes. So again in this scenario, if the normal force is equal to the gravitational force, so you know that the gravitational force is equal to mg, which is also equal to our weight. Okay, yes, so mg, this m stands for the mass of an object, okay, and this g is called the gravitational force. Okay, yes, which is 9,8. okay, yes. So in order for you to calculate the gravitational force acting on an object, you have to take its mass multiplied by 9,8, as well as to the normal force, because the normal force, you can see that the normal force is equal to the gravitational force. Yes, that's how it goes. Yes, so we're going to be dealing with situations like this, but I just want to let you know in the early stages so that you don't get confused. Okay, yes, so let's move to the calculations. Okay, so we have this scenario here. We have this scenario here. This is our box, okay, which is 20 kg. Let's say this is 20 kg. The applied force, okay, so this is the surface, okay. The applied force, this is the applied force, is equal to 60 newtons, okay, which is equal to 60 newtons. So these are the questions. Draw a free body diagram. Draw a free body diagram. So question number 2 says, let's calculate the acceleration, okay. Calculate the acceleration. So our question number 3 says, let's calculate the frictional force. No, okay, let's wait there, okay, because there's no friction here, okay. Let's say that no friction acting on this object, okay. Yes, there's no friction, meaning that this surface is very smooth. There's no friction acting on it, or there is no opposing force. Okay, so for us to calculate, so let's first draw a free body diagram, okay, for all the forces that are acting on this object. So again, guys, there's a difference between a free body diagram and a force diagram. A free body diagram, this is a free body diagram. Just use a dot, okay. This is number 1. We're answering number 1. These are the answers, okay. These are the answers. So to draw a free body diagram, you don't draw a box, okay, just like a force diagram. So this is the free body diagram. We draw a dot, so you should read, okay, free body diagram or a force diagram. So a force diagram, you're going to draw this 20 kg and show all the forces acting on it, just like a free body diagram. But a free body diagram, you put a dot instead of drawing a box. I think I've nailed that. So let's start. So when you are showing all the forces, you must start from the point, okay. Yes, and the dot must be quite bigger, because there might be forces that are acting on the same side, okay. So yes, so this is the applied force this way, okay. This is your applied force, okay. Yes, you can also write, you can also show it's equals to 60 newtons, or you can just write applied force, okay. Yes, so also this box is not flying, it's on the surface, meaning that there is a gravitational force acting on it, okay. Yes, it's on the surface. There's a gravitational force, so there's a gravitational force which is equals to mg, which is equals to weight, okay. Yes, so there is also in this object a normal force. If there's a gravitational force, there's also a normal force on the ground, okay, or on the surface. So this is the normal force. So these are all forces acting on this subject. So for your number 1, you're correct. Where's my other color? Can't see my other color, guys. Okay, I think I found it. Find my other color. Okay, so this is correct, this is correct, this is correct, this is correct, okay. Yes, again, your lines or your vectors must start from this point, from the point, okay. Yes, so that's how it goes. Okay, moving to number 2, which says calculate the acceleration. Okay, your calculators must now be ready. Okay, yes, calculate the acceleration. So you know that our formula is the net force, or F net, or F res, okay, resultant force or the net force. Okay, yes, is equals to ma. So by just emphasizing the net force, it can also be the same as F res. Okay, so don't get surprised when you see F res. So this is the resultant force, all the forces. Okay, all the forces, the net force, all the forces, the same thing. Okay, yes, so you can say F res or F net. So F net is equals to ma. So you know that the net force is equals to ma, the mass of that object is 20 kg, multiplied by so the net force is 60. The net force is 60, so sorry, net force is 60, so the net force is equals to ma. So we have 60, the net force, all the forces acting on that object, 60 newtons, is equals to, the mass of this object is 20 kg multiplied by a. Okay, yes, so let's divide so that you can get the acceleration. Okay, by 20 by 20, so this 20 cancel this 20, we left with acceleration. So our acceleration is equal to 60 divided by 20, this becomes 33 meters per second. 3 meters per second. I should have used my calculator, guys. Okay, so always use the calculator. So 60 divide by 30 by 20, I mean 60 divide, what is my division? Let's divide by 20, it becomes 3. Okay, yes, so 60, so that's our acceleration. So our acceleration is correct. So meters per second, so sorry, this is per second. I'm full of mistakes right now, don't know what's going on. Okay, so this is correct. This is the substitutions are correct. Net force, these are the forces, was 60, the 20, which is the mass of that object, the acceleration. So you made this, this is calculations, and your answer is correct. Okay, yes, that's how it goes. So let's say now this surface has a friction. So let's say it has a friction right now. Okay, yes. So if now it has a friction, okay, let's say there's nothing that we change, we just say there's a friction here. Okay, and the friction or the roughness, okay, the roughness here, okay, so that you don't get confused, let me just write a new one. Okay, yes, let me use a new one. So we have our 20 kg block here. Okay, 20 kg block, this is 20 kg. 20 kg, this is 20 kg block. And now this is rough. Okay, the surface is now rough, and our force is still our 60 newtons. The applied force is 60 newtons, Okay, so the question says, okay, so the friction here, or the roughness of the surface, mu is equals to, is it 0. Let's say it's 0.4. Okay, let's say it's 0.04. So this is the roughness. Okay, it's 0.4. So the very first question again says calculate the friction of the object. Okay, yes, of the object, or the friction experienced by the object by moving. Okay, yes, so that's how it goes. So the second one will say calculate the acceleration with the presence of friction. Okay, mind you, they say now we must calculate the acceleration with the presence of friction. And again, mind you, we already calculated the acceleration for this scenario. Okay, but now there is a friction, meaning that if there is a friction now, the object is going to move slower. Okay, yes. Okay, so let's calculate the friction of the object. So we are given mu. Okay, the coefficient of the frictional force is 0.4, the roughness. Okay, so this basically means that, and this object is moving. Okay, yes. Okay, so this is now kinetic frictional force. Okay, so these are our answers. Okay, we're answering now. So our answer for number 1 will be like, let's use the formula for a kinetic frictional force is equals to UK, okay, UK normal force. Okay, but the normal force is not given. How are we going to look for the normal force? So firstly, we must check for the normal force and substitute mu so that we can get the kinetic frictional force. Okay, so working on the side for the normal force, so we're looking for the normal force right now. The normal force, for the normal force, okay, yes, so sorry. So right now we're looking for the normal force. So mind you, normal force is also equal to the gravity. Okay, so the normal force is equal to the gravitational force. This basically means that Fn is equal to Ft, which is equal to mg. Okay, so our normal force is equal to Ft, which is equal to the mass of that object is 20 kg multiplied by the gravity. I said 9.8, if you still remember. So it's always 9.8 for gravity, guys. Okay, yes. So our normal force will be equal to the gravitational force, which is equal to 20. Let's multiply in our calculators, guys. Let's say 20 multiplied by 9.8 multiplied by 9.8. That's give us 196. Okay, yes. 196 newtons. Okay, so our normal force is 196 newtons. So this is equals to 0,4 196. Okay, this is equals to 0,4 multiplied by 196. Press in your calculators, guys. So 0,4 multiplied by 196. It's 78,4. Okay, yes. Okay, meaning that it's 78,4 newtons. That's how it goes. So yes, again, maybe you're asking yourself, why is it's our kinetic frictional force or our frictional force greater than the applied force if the object is moving? So now, since because this is my mistake, made a mistake here, but not a mistake. Yes, our calculations are correct, our substitutions are correct, everything is correct, the scenario is correct. But now I should have, at least since I made this up for myself, okay, 20 kg block and this force that is being applied on it, I made this by myself. Okay, these are not coming somewhere. Okay, yes, because when I'm checking right now, hey, our frictional force is greater than, but I said this object was moving. But let's assume, guys, yeah, let's assume it's static frictional force. Okay, yes, let's assume it's static frictional force. Let's just make it easy and change here. Static frictional force. Okay, yes, this is our static frictional force on its maximum. Okay, so again, this obliged us to understand other concepts under this diagram or under this scenario again. So if our static frictional force is 78,4 newtons and our applied force there, it's 60 newtons, this basically means that this object is not moving, meaning that the maximum static frictional force hasn't been overcome. Okay, yes, so the maximum static frictional force, it's this 78. Okay, yes, this is the F max. Okay, yes, statics. Okay, so if the maximum frictional force, static frictional force, hasn't been reached, okay, the object will still remain at rest. But if my applied force is now maybe 80 newtons or 79 newtons or 80 newtons, the object will suddenly move, or will begin to move. I think you get me. So that's how it goes. So now I was going to say, let's calculate the acceleration with the presence of the friction. But let's say our block, it's 10 newtons. Okay, it's 10 kg, and our applied force is 60 again. Okay, yes. So because it's obvious that our solution is going to be negative. Okay, yes. Okay, so let's say this is, we have a block that is 10 kg. Okay, our 10 kg block is our 10 kg block being pulled this way by 60 newtons, and our the roughness, let's say it's 0,2. The roughness is equal to 0,2. Okay, yes. So let's calculate the friction of the object, of this object, and calculate the acceleration of this object. Okay, yes. So let's calculate so these are our answers using the very same question upwards. Okay, so for number 1, okay, let me move paper a little bit so that I can see. Okay, so calculate the friction of the object. So the friction of the object, you know that we have this, okay, yes, and the friction is, okay, the object is moving, kinetic frictional force. So the roughness, okay, yes, this is rough. So let's say, okay, so let's go look for our normal force. So our normal force is going to be okay, since we already did it, okay, let me do it again. So our normal force is equal to gravitational force, okay? So our normal force is equal to gravitational force is equal to mt, is equal to the weight. So our normal force is equal to Fc, which is equal to 10 multiplied by 9,8. So our normal force is equal to gravitational force. So let's press into our calculators, guys. So 10 multiplied by 9,8, that's equals to 98. That's equals to 98 newtons, okay? That's equals to 98 newtons. Again, it's bigger than our applied force, okay? Yes. So okay, so that was the friction upwards, okay? So okay, this is going to be okay, this is going to be, to get our friction, we have to multiply 0, something 0,2, okay? So 0,2 to get our friction with 98, okay? With 98, our normal force, okay? So let's multiply 0,2 by 98 newtons. So 0,2, so 0,2 multiplied by 98, it gives us 19,6 newtons. So that gives us 19,6 newtons. So right now it gives us a friction, kinetic friction, that is lower than the applied force, meaning that this object is moving right now. The roughness is lower, so that's why now we get a lower friction, okay? Yes, and now our applied force is more than a friction, meaning that this object is moving. Okay, so to answer number two was saying calculate the acceleration with the presence of friction or with the presence of frictional force. Okay, so now we're calculating the acceleration. So you know that the net force is equal to ma, okay, mass times acceleration. So the net force, okay, our net force, which force is acting there, is the applied force, which is equal to 60, okay, plus the frictional force, okay, that is acting there, okay, in this way, okay. There's a frictional force acting in this way here. This is the frictional force, okay, and the static frictional force, I mean the kinetic frictional force. So you know, if this is opposing the ocean, the motion is going to be minus. Okay, the frictional force is minus. So this is going to be equal to mass times A. So our mass is 10. We don't know our acceleration. So this becomes, let's substitute, this is our 60 plus minus what? 19,6 newtons. Okay, yes. So this is equals to 10A. So our 60 minus 19,6 newtons is equals to 10A. So let's calculate on our calculators. 60 minus 19,6. So our 60 minus 19,6. That's 40,4 newtons. Okay, that's 40,4 is equals to 10A. So now let's divide by 10. Okay, let's go this side, this way. So let's say 40,4 is equals to 10A. Let's divide by 10. Let's divide by 10. So, and therefore our acceleration is equal to, so let's divide 40,4. Okay, 40,4. Okay, 40,4 divide by 10. That gives us 4,04 meters per second. So 4,04 meters. Okay, meters per second squared. Okay, that's how it goes. So this is our answer. Okay, I think you get it, guys. I'm so sorry for writing so dead. Okay, yes. Let's move to the other scenario. So sorry. So do like this. Okay, so this scenario is our scenario 2. Okay, so we have our 10 kg, but now we are going to focus on the vertical forces. This is our 10 kg. This is the force that is being applied, which is 160 newtons. Okay, which is equal to 160 newtons. Okay, so the very first question says draw a free body diagram. Draw a free body diagram. Okay, the second one says let's calculate the acceleration. Calculate the acceleration. Okay, guys, please forgive me with my bad writing and my bad calculations and so on. So sorry, please forgive me. Okay, yes. So let's draw a free body diagram for this object. Okay, yes. Okay, these are our answers. Okay, our answers for number 1. So by answering number 1, drawing a free body diagram, let's go. Okay, this is our dot, which represents the position of our object. There is a force acting upwards, okay, on it, meaning that there's someone who's lifting this by 160 newtons. Okay, there's someone who's lifting this object by 160 newtons. Okay, this is the applied force, which is equal to 160 newtons. Okay, so okay, if you are pulling, okay, something upwards, the gravitational force is opposing. Okay, yes. So the gravitational force, because this thing is weight. Okay, yes, gravitational force is opposite. Okay, again, look for your magnitude, guys. Okay, the length of your vectors, okay, when showing the forces. So the magnitude of this one must be longer than this one, okay, must be longer. I'm so sorry, must be longer, and this one must be at least shorter. The gravitational part, okay, must be shorter. So this is our Fg is equal to mg, okay. Yes. So again, maybe you think, okay, so we're done, okay, we're done. So we're done drawing our free body diagram. So you maybe you're asking yourself, hey, say, why now this if we have gravitational force, where is our normal force? The normal force is only applied, or yes, is only applied when an object is on the surface, okay. There's no normal force right now. The object is in the air, okay. Yes, but only the gravitational force acting downwards, okay. Yes. Okay, it's called weight, okay. Yes, weight. That's how it goes, okay. Let's go and correct, okay. Got it right, or vector, got it right, okay. Everything is correct. So the question number 2 says you must calculate the acceleration, right? Yes. So to answer number 2, to answer number 2, you know that our net force is equals to ma, okay. When you have to do calculations, this is the only formula that you use, okay. Yes, under these Newton's laws. When calculating acceleration, the mass and other forces like the applied force, etc. But for your friction, normal force, your tension, and so on, yes, you also apply them. But for your tension, your applied force, and so on, they're under here. But the friction also has its own formula, but only when you are given the coefficient, okay, of the frictional force. Okay, moving. So our net force is 160 newtons. Our mass is 10. Our acceleration, we don't know. So over 10 over 10. So therefore our acceleration is equal to, so 160 divided by 10, okay. 160 divided by 10. So 160 newtons. So sorry for delays. 160 newtons divided by 10. That gives us 16 meters per second. Okay, second squared. 16 meters per second squared. Okay, so this is that's how it goes. Okay, that's how it goes. So yes, so let's have another scenario. Okay, okay, so let's say this is scenario 3. Okay, yes, so we have our 10 kg block. Okay, our 10 kg block being pulled, okay, by this beautiful 15 kg block. Okay, 15 kg block, okay, in a horizontal surface. Okay, okay, so let's say this is box X, this is box Y, okay, and this is the tension here. This is an inextensible string, okay, inextensible string, this one, okay, yes, and our force that is being applied is 500 newtons. Okay, 500 newtons. Okay, so our very first question says okay, again, the friction that is being experienced there at box X, okay, it's this is coefficient of the friction at box X is 0, it's 0,3. Okay, let's say it's 0,3, and the friction that is being experienced, this is for X, this is for X, and for Y. For Y, the friction that is being experienced there is 0,4. It's 0,4. Okay. Yes. So the surface is frictionless. Okay. Yes. Okay. No. The surface it has the presence of friction. Okay. Yes. Okay. So so our very first question says, let's draw a feedback diagram for Y. Draw. I'm trying, guys, to repeat for writing. Draw a free body diagram for Y. Okay. Yes, let's try a free body diagram for Y. Our second question says, let's calculate the friction for body X and Y. Let's calculate the friction for body X and Y. Okay. Body X and Y. Our third question is the last one, I believe. We can say, let's calculate the acceleration and tension. Okay. Calculate let's say A, acceleration, okay, and B, tension there. Okay. Yes, between X and Y. Okay, so let's answer the questions now. So let's draw the free body diagram for Y. Okay, if you're drawing the free body diagram for Y, okay, these are our answers. We're answering now, starting from number 1. Okay, these are our answers. So free body diagram for Y. And this must be quite big, okay, because there will be forces that are going to the same direction now. Okay, for Y, you can see there's applied force there. Okay, we have our applied force, which is equal to 500 newtons. Okay, there's no need to distinguish, okay, or to show the force. Okay, yes, which is 500 newtons. Okay, but I'm just writing. We also have to, okay, so we also have gravitational force, because it's on the surface, okay, acting on it, okay, which is equals to weight, okay, and we also have our normal force being at equilibrium with the gravitational force. So there's a friction there, kinetic frictional force. Okay, yes, so there's a kinetic frictional force acting on that side. Okay, so this is our kinetic frictional force. okay, or kinetic frictional force. And also, as this object 15 kg block is moving to the right hand side, pulled by 500 newtons, is also experiencing tension to the left hand side, okay, yes, because it's pulling x. So meaning that if y is pulling x, then also x is also pulling y. Newton's third law, come on, okay, yes. So we're also experiencing here our tension force, okay, or Ft is our tension force. So that's how it goes. I think I wrote all the forces needed there that are acting on that particular object, okay. I'm looking for my pen, okay. So the normal force is there, okay, acting perpendicular from the ground, gravitational force acting downwards, the force applied, the tension between x and y, and the kinetic frictional force acting parallel to the ground. Yeah. So that's how it goes. That's how easy it is, okay? Yes. So that was our very first question being answered. So let's move to the second question right now, which says calculate the friction for body X and body Y as well. Okay. So for number two is very easy. So okay, so this is for let's start for X. Okay, start for X. So we're calculating for X now, okay. So we're going to say mu normal force, okay, yes. So this basically means that our coefficient is there. We have our coefficient being 0.3. So this equals to 0.3. Our normal force, dololo. So we have to go and find our normal force. So okay, remind you, our normal force equals to gravitational force. So our normal force is equal to gravitational force, which is equal to mg. So our normal force is equal to, so sorry for not being straight, okay. Let me try to be straight. Gravitational force, which is equal to mass times gravity, that's 10 multiplied by 9.8. So our normal force, therefore our normal force is equal to gravity, which is equal to 10 multiplied by 9.8. Let's go into our calculators. So let's say 10 multiplied by 9.8, that's equals to 98. Okay, it's equals to 98. So our normal force is 98. So 0.3 multiplied by 98 to find our kinetic frictional force for body X. So 0.3 multiply by 98, that's 29.4 newtons. Okay, so 29.4 newtons. Okay, that's our kinetic frictional force for body X. Okay, yes, for that 10 kg block. So that 10 kg block is experiencing a friction of 29.4 newtons. Okay, let's calculate for y now. Okay, so like this. I think we can try to calculate for y in this space. I don't think so. Okay, let's say like this. Okay, so now we're calculating for y. So our kinetic frictional force is equals to mu normal force. So our kinetic frictional force is equals to that's 0.4 for y, and our n to below. Let's go and calculate our n. Our normal force. So this is your normal force is equals to gravitational force. So meaning that your normal force is equals to gravitational force is equals to mass times gravity. So normal force is equals to gravity, which is equals to, what's the mass? It's 15 multiplied by what? Multiplied by 9,8. Okay, so our normal force is equals to, therefore normal force equals to gravity, which is equals to 15 multiplied by 9,8. 15 multiplied by 9,8. Okay, that becomes 147 newtons. 147 newtons. Okay, yes, that's how it goes. Okay, 147. So sorry, 147. Okay, also use your calculators, guys. I might be wrong. Okay, I might press something wrong. Okay, yes, so please try to use your calculators. Okay, let's multiply 0,4 multiplied by 147. So 0,4 multiplied by 147. Okay, 147. That's 58,8. Okay, that's 58,8. I'm not sure if my calculator is rounding off correctly. Okay, yes, and please try to round off correctly, guys, during your examinations mostly, because you might be penalized, or you are going to penalize. Okay, so this is it. This is the answer for our number 2. Okay, which are both correct. Okay, it's correct. You have to calculate for the normal force so that you can substitute. So okay, we have to calculate for the normal force so that you can substitute here. Yes, so everything is correct. So you're passing, guys. Let's jump to now our number 3. Okay, so our number 3 is also calculate the acceleration, which is our A, and our question B says tension. Okay, this is whereby the confusion starts. Okay, but this is not confusion, this is a little thing, guys. Okay, please believe me. Okay, so our number 3 to answer, our number 3, calculate the acceleration for our A. Okay, for acceleration. So okay, you know, net force, or F net, is equals to ma, which are the forces that are acting, calculating for the acceleration. Yeah, so sorry. Okay, okay, so let's look at okay, so let's start with x. Yes, okay, so this is the F net is equals to ma, so this is for x. Okay, for x. Okay, yes, for x, F net is equals to ma. Which are the forces acting on x? So on x, there's a frictional force acting on it, which is equals to 29,4 newtons, and there is an applied force. Okay, but the applied force is only acting on y. There's also a tension force, so which is going to the same side as the applied force, meaning that our tension is positive. So our tension plus, okay, plus our frictional force, okay, our kinetic frictional force, okay, is equals to MA. The mass is 10 A. We don't know this acceleration looking for. Okay, so our tension, okay, our tension we don't know, plus, okay, it's going to be minus, okay, plus negative 29,4 is equal to 10A. So T minus 29,4 is equal to 10A. So no like terms, okay, so this becomes our very first equation. Okay, I think we are all, guys. Okay, again, we're looking for y right now. Say y this side. So for y, our net force is equal to MA. So which are the forces that are acting on y there? So the forces acting on y there is the applied force. The applied force, which is 500 newtons. The tension force, okay, which is acting, plus the tension force, which is acting in the opposite direction, okay, yes, which is acting that way, okay, pulling y, okay, yes, being pulled by x, by the way. So it's equals to our MA. Okay, so our applied force is 500 plus negative T, our tension, so our mass is 15 multiplied by A. Okay, so this becomes 500 plus minus, okay, so sorry, this is minus T is equals to 15A. This becomes our second equation, okay? This is our second equation, okay? So let's oh no, there was a friction acting on y, okay? There was a friction acting on y, okay? Let's just cancel that one and calculate for the friction acting on y. So for y, okay, so let's say for y the net force is equals to MA. Okay, so we have the applied force. Plus which is minus our F, okay, minus T, okay, is equal to MA. So 500 minus what was our, okay, 58,8 minus T is equal to, what's our mass? Our mass is 15 A, okay, yes. So 500 minus 58,8. Let's press our calculators. Okay, so 500 minus 58,8. That becomes 441,2. Okay, that becomes 441,2. 441,2 minus T is equal to 15A. and this becomes our second equation. Okay, so now let's find our acceleration by looking for the like terms in our equations. So since this is our very first equation, t minus 29,4 is equals to 10a, so 441,2 for our second equation, minus t is equals to 15a. Okay, this is equation 1, this is equation 2. Okay, so let's go look for okay, 10 plus 15, go to calculator. So 10, 15 plus 10, that becomes 25. Okay, 25a. So this is positive tension minus this negative tension, cancel each other. So 441,2 minus 29,4. So let's go and calculate. 441,2 minus, okay, minus 29,4. 29,4 minus 29,4, it gives us 411,8. okay, 411,8, okay, over 25 over 25. So this cancels. So 414,8 divided by 25. So 414, 8 divided by 25. That gives us 16,59 meters per second. Okay, our acceleration, therefore acceleration is equals to 16,59 meters. I'm sorry, acceleration is equals to meters per second. Okay, that's how it goes, guys. Okay, we have to calculate the tension right now. So in order for you to determine the tension, you can either use our original formula, but the easiest way is to substitute from any equation here. Okay, substitute the acceleration so that you can get the tension, because the tension is the same from both objects. Okay, let's substitute. Let's say you calculate the tension here, okay, which was our number 3, right? Our number 3b. So the tension, let's use this one for equation 2. Okay, 441,2 minus tension is equals to 15a. So 441,2 minus tension is equals to 15 multiplied by 16,59. Okay, so let's multiply 15 multiply by 16,59. So 15 multiplied by 16,59. Okay, it becomes 248.85. So 441.2 minus t is equals to 248. 248.85. Okay, so this is like this. So we have our negative t here is equals to so 248.85 minus 441.2. So let's say 248.85 minus 441.2, it becomes negative 192. Negative t is equals to negative 192.35. Therefore our t is equals to 192.35. Okay, yes, they divide each other by negative 1 by negative 1. That's why you have a positive answer. Okay, so this is our answer. T is equals to 192.35 newtons. Okay, 35 newtons. Okay, yes, that's how it goes, guys. I think we are done for now. Okay, yes, because I wanted us to continue, but I will make other exercises, other activities in the next following video, because time is ticking. Thank you so much for your time, to those who watched, and please, again, don't forget to subscribe, guys. Physical science and the science of physics is very, very easy, guys. I'll be with you the whole year this year, until you write your examinations. I'll be helping, I'll be exploiting myself much as I can, so that you can get your own desirable results. See you again. Don't forget to subscribe. Cheers.